All right, so, well, now we do understand a lot more than we used to about stress-strain curve. And in particular, we've introduced the true and engineering stress-strain curves. Now, in the homeworks, you are going to employ both of them. What you should remember at this stage is that if the deformations are small, in other words, if the strains are small, there is no distinction between true or engineering stress or true and engineering strain. They are approximately the same. If the deformations are significantly large, and this is certainly the case in the vicinity of the necking region and beyond necking, then you have to use for practical purposes true stress and strain. I'm going to comment on this once again in the upcoming example. But for now, what we would like to do is we would like to be able to model stress-strain curve. Now, these models are intrinsically, to some extent at least, directed or meant to be used with the true stress-strain curve, but what I'm going to employ underneath now is the engineering stress-strain curve. I'm just going to write sigma and epsilon. Just remember, everything that I do without any modification almost is going to be applicable to the true stress-strain curve. In other words, if you want to carry out the modeling steps that I will describe shortly in terms of true stress and strain, just replace epsilon with epsilon tilde and sigma with sigma tilde, and the procedure remains exactly the same. That's the way you're going to solve the homework problem. So presently, however, I'm going to stick to the engineering stress and strain. Now, what is our goal? Now, our goal is to be able to model the stress-strain curve, and let me tell you why. Now, first of all, what we are able to do now is we are able to observe or convert the experimental measurements to the stress-strain curve. Now, the way that conversion occurs, of course, I'm going to eventually draw a line, but really what is happening on the background is we have a machine, and the machine takes measurements of length change versus load at various stages of loading, and then divide by the initial area and length, you obtain engineering stress and strain curve. That's our raw piece of information. We start with that raw piece of information, and if necessary, we convert it to the true stress and strain curve. But our raw data is essentially load versus length change or engineering stress and strain. So now the machine sends us that at zero strain, let's say there's zero stress, you increase the strain, you increase the stress, you measure a larger load, and this way you have many points. Okay, and there might be more points eventually, so the data does actually perhaps continue. But really you have tons of points, and what on the background the plot is doing when you play with that data, when you, let's say, have a data sheet and you plot it, you have so many points that you virtually, when you connect them with tiny lines, right, you observe a curve, which is our engineering stress-strain curve, right? But what we would really like to do now is think of sparse data. In other words, perhaps I don't have so many data measurements, or the way I do the experiment, I'd like to be able to reproduce the stress-strain curve only from a few set of measurements. Okay, there can be different motivations for this. I'm going to exaggerate. In practice, you take hundreds of data points, but I'm going to assume that we don't take that many points. I'm going to take just like, let's say, 10 points. And now, if I connect these points with one another with straight lines, it's not going to look nice. So instead, what I'd like to have is I'd like to have a stress-strain curve, a smooth line that is able to replicate this data as closely as possible. So this is our data. and I'd like to replicate that as well as possible. And the way you do that mathematically is you take an expression that relates stress to strain. So stress is going to be a function of strain. That function might be a polynomial function. It can be a more complicated function. It can have logarithms, whatever. But in the end, it will have some free parameters. I will determine those free parameters carefully, and I will have an expression that relates stress to strain as well as possible in the sense that my fit, which is my model, replicates the true data as closely as possible. Okay. Now, why do I want to do this? Now, my fit does not need to be imperfect. Here I have assumed that the fit is imperfect. It can be a very good fit to the data. I can certainly do that as well. Here I've exaggerated in order to emphasize the fact that in general modeling always involves some error. Error with respect to the experimental data. Measurement for sure also has some error, but once you have your data and you'd like to be able to reproduce that data with some mathematical expression such that you give me the strain, I tell you what the stress is, that's our modeling step, and that modeling step is going to involve an additional error. In other words, you're not going to be reproduce the actual value at a given value of strain, the actual value of stress, but you're going to make an error and measure something different, right? So at that value, for instance, okay, that's what I would like to measure or calculate, but in reality I can calculate that because my model is imperfect. However, my model also has an advantage, namely that there is no data point, let's say, between these two measurement points, but my model is able to deliver me a value of the stress at any given value of epsilon. So the advantage of the model is you give me any value of epsilon, not necessarily those that have to do with the data points. I can give you the corresponding value of stress. So it can estimate, interpolate in a clever fashion the values of the given values of the stress by making use of our corresponding strain values. All right, so why do I need a model? Well, because the stress-strain curve gives me information about the stress, engineering stress at a given engineering strain. Engineering strain is deformation, engineering stress is load. So this curve, in other words, this nice mathematical function between deformation and load is going to help me design procedures that are typically, for instance, used in manufacturing operations. In manufacturing operations, you rarely remain in the elastic region. You take a piece of, let's say, aluminum sheet, you want to form it into the shape of the car hull or the car door or whatever. So those are operations that involve plastic deformations, and if you want to design those operations and the machines that carry out those operations, you would like to be able to estimate the amount of load that is required to deform a raw material, say a sheet, into the shape of the car door, right? So that's a plastic deformation. I like to be able to estimate the amount of load that goes into it. That deformation is in the plastic region, so I need a function that can tell me, given a certain amount of deformation that's in the plastic region, what is the corresponding load that I need to apply, right? And if you know those loads, then you can determine your manufacturing operations and the machines that carry it out properly within certain safety factors, of course. So the model is going to help me take that material behavior, which is in reality represented by data, but it's at a discrete set of points. I'm going to be able to take that behavior and put it into actually some process analysis. So it's useful to be able to fit functions, models into given data, and that's what we are going to try and do next. Now, before we do so, let us make a number of observations that are going to be helpful. Again, I am presently, as I said, assuming engineering stress versus strain, but you can do everything that I am saying in the using true stress and strain as well. So I'm going to look at a portion of the stress-strain curve, let's say, which goes like that, right? Well, just for the sake of our present discussion, let me idealize it a little bit. Let's idealize it as having a somewhat distinct transition to yielding. It doesn't have to, but just for present purposes, I've assumed it does. So that is probably where the material starts to yield. That is sigma naught. And this portion is completely elastic. And therefore, I know that in this portion of the curve, what I have is a relation between stress and strain as follows, right? Now, this is a model as well. It's the Hooke's law. Given a value of epsilon, I can tell you what the stress is if you tell me what the constant of proportionality is. That's in essence what we're going to try to do in the plastic portion as well, but the complication there is that the relation is not linear, so it's going to be a different function. But in the elastic region, that there is no such complication. Everything is fairly clear. Now, then, what I can do is I can, of course, start. Now, how do I get that curve? I have the raw specimen, and I start loading it. And I can load it up to an intermediate point here. If I unload it, it will go back to zero stress and strain. That's going to be exactly what I'm going to be observing all the way up to yielding. But beyond yielding, something else is going to happen. Say I go up to that point, and if at that point I unload, I observe two things. One, I unload on a curve that is virtually parallel to the initial one. So in other words, the slope here is 1 to e. So I'm going to make use of that information. Now then, what I also observe is that when I unload fully, in other words, I remove all the load, there's going to be some remnant or permanent deformation remaining. That permanent strain is going to be called the plastic strain, epsilon p. Now, at this stage, you might ask, well, what would have happened if I loaded back the specimen? Well, what would happen, again, this is an idealization, but what would happen is you would load the specimen back up, you would move back up on the same curve. In reality, there is a small deviation at some point, but if I idealize it, you will load back up on the same curve. When you come to the point of yielding, the specimen will continue along the same line. So in other words, if I took a single shot, the specimen would go like that. Okay. If I did an unloading, it would come back. If I load it back again, it would come back up along the same line, hit that initial point where I started unloading, and then continue as if nothing had happened. Okay, so that's the way loading and unloading will work. Now, what I can realize is that at that point, the total strain is epsilon. So when I unload, some portion of the deformation has been recovered, and that is the elastic strain. And therefore, I have an important piece of information. The total strain is the sum of the elastic and plastic portions. Okay. This is always true. Now, this is always true, so the total strain is composed of elastic and plastic portions, but there may not always be a plastic portion. So for instance, in this region along the stress strain curve, all the deformations are elastic. There is no plastic strain. So in that initial portion, sigma is equal to E times epsilon or epsilon E, because they are the same, because epsilon P is equal to 0. But that's not the case beyond the point of yielding. Beyond the point of yielding, you now start to have some plastic strain. But at that point, when I try to unload, I see that I unload on a curve that is parallel to the initial one. And now that was the point where I started unloading, and that's where I have a value of stress, say sigma. If I'd like to calculate the value of sigma, well, what I observe is that, well, that distance is epsilon E, the slope is E, and therefore sigma is simply equal to E times epsilon E, the elastic portion of the strain. Again, these are relations, the ones in the boxes, that we need to know, and that relation is also always true. Okay? Now, sigma is always E times epsilon E, but it is also equal to E times epsilon within that initial portion where there is no yielding. So this relation, the blue relation, is true up to yielding, but the relation in the box is always true, right? In the initial purely elastic zone, a total strain is equal to the elastic strain, so the two relations are identical. But the one that's always true is that one and not that relation. So sigma equals E epsilon, not the elastic strain, but the total strain, is something that's valid for deformations where plasticity has not occurred yet. So what I can also, of course, do is I can write that relation, the same relation as E, by extracting epsilon E from that relation, which is epsilon minus epsilon P. I can write that relation as such. Okay. So therefore, I know that if I give you the total strain, and if you know the amount of plastic strain, then you can find the elastic strain, epsilon minus epsilon P, multiply it with the Young's modulus, and you get the stress. All right, good. So these are observations and definitions that we have made. What is the motivation behind all of this? Well, if I unload at any stage, there's going to be some permanent deformation and elastically recovered deformation. So the total strain is decomposed into elastic and plastic parts. This is always true. And moreover, if I'd like to calculate the stress at any point, unloading is always elastic. So that's the message here. Unloading is elastic, and therefore the stress is always equal to the Young's modulus times the total elastic strain. Okay, so that's also always true. But now, remember, what I'm trying to do is I'm trying to model the stress-strain curve. In other words, you give me the value of strain and I tell you what the stress is. That's my goal. Why do I want to do that? Because I want a model. Why do I need a model? Because eventually if I'd like to design something in a manufacturing experiment, or if I'd like to understand how a car, let's say in a crash test, is going to, what kind of loads and stresses it's going to experience for a given amount of plastic deformation, I'd like to be able to predict the amount of corresponding stress. And for that, I need this model. And that model requires that you give me the value of strain, I tell you what the stress is. Strain, stress. Okay. Now, what do I have presently? You give me the strain, that's epsilon, and I want to tell you what the stress is. Well, I know what the Young's modulus is, but at a given stage of loading, unless I know what the plastic strain is, I cannot tell you what the stress is, because I have to subtract the plastic strain from the total strain in order to find the elastic strain, and then I can multiply it with the Young's modulus and tell you what the stress is. So if I want to carry out a model, we have to realize that the key piece of missing information is the plastic strain. Okay, so our modeling effort is going to implicitly address that difficulty. You give me a certain deformation. Well, at a given value of epsilon, what is the plastic strain? How can I find it so that I can subtract that amount of plastic strain from the total strain, multiply it with E, let's say, and find what the stress is. So our efforts are going to next go into determination of the plastic strain, so that you give me the value of epsilon and I can tell you through that knowledge what the value of stress is, and that completes eventually my model. Okay, so when we do that modeling, we're going to be talking about hardening. Okay, now hardening is something you have already seen, but perhaps I have not explicitly given it a name. But now we can give it a name, and I can explain the concept as follows. Well, first of all, we have, remember, the concept of elastic and perfectly plastic material behavior. So it's elastic and then perfectly plastic. Perfectly plastic in the sense that the stress does not increase further, it remains at a constant value, and that's what you observe all the way up to failure. And one motivation, as we've mentioned before, is single crystal metals. That's almost how they behave. But that's not what I observe for real metals in application. What I observe is a curve that looks different. Now, this curve is a curve that is set to display hardening. So, plasticity with hardening. Hardening because it gets harder at every step to deform the material further. Let's look at the perfectly plastic case once again. The engineering stress is load over area. I come to the point of yielding, which is sigma naught, and I want to deform the material further. All I have to do is pull on it. The amount of load does not change because, remember, this is the engineering stress, load over initial area. The amount of load that I need to apply really doesn't change. I keep pulling on it, right? Now, when I look at the stress for the case of hardening, I come to the point of yielding, and I want to deform the material further. To deform the material further, it's not sufficient that I apply the same amount of stress or load. I have to increase it. So the material starts to become harder to deform. Do I want to deform it further? Well, you have to increase the stress further. Do you want to deform it further? You have to increase it yet further. So every time you want to increase the deformation, you have to increase also the load along with it. So that's the concept of hardening. With deformation, the material becomes, if you like, harder to deform. That's my, if you like, take on this terminology. Okay. So, well, how do I observe hardening and why is it important? Well, I can give you a very simple example that comes also from the stress strain curve. So what I'm trying to do here is I'm trying to emphasize that in reality, the material really becomes harder to deform as you actually go into the plastic region. So to explain that, what I'm going to do is I'm going to take a specimen and I'm going to call it the raw specimen. Let's call that specimen A. And I will take that specimen and I will pull on it all the way up to failure. I can do this more easily with the true stress strain curve, but I'll stick to the engineering stress strain curve and I'm not really drawing the portion that is associated with necking. Let's say, in fact, that's the way the stress strain curve goes and ends for this particular specimen. So I take the specimen and I break it, right? That's one thing I can certainly do. Now let's imagine that I have several of those specimens. It's exactly the same material, exactly the same shape, cross-sectional area, whatever, and I call them A, B, C, D eventually. That's what I want to do. And the first specimen, I take specimen A, I pull on it and I break it. The second specimen, what I do is I proceed as if I'm loading it along the, or as if I'm going to break it. So I load it. It's the same specimen, so it behaves in the same fashion. But what I'm going to do is, at some point, I'm going to unload, not break it, but unload it. And I'm going to come back to this point. Okay. This is going to be my specimen B. Now then I take the third specimen. It's going to be called eventually specimen C. Again, I start along the same curve. It's the same specimen. It goes on the same curve. But instead of breaking it, I'm going to load it up to a certain point that is beyond the green specimen, specimen B. And then I'm going to unload it again. And I'm going to call that specimen C. Okay. So then I will compare the behaviors, the stress strain behaviors of these three specimens. So in the following manner. So here there's going to be a little bit of exaggeration and idealization, but that is sufficient to make the point. So first of all, I am going to look at specimen A. Now, specimen A is the raw specimen. I've taken it and I have deformed it all the way to failure. Okay, that was specimen A. And then I took that specimen, the same specimen, and I loaded it, but before I broke it, I unloaded it, and that is now an unbroken specimen. It has been loaded up to a certain stage, but it's not broken yet. So then I unloaded it, and I have now a unbroken specimen, but it's not the raw specimen. The raw specimen is A. It has been deformed plastically to a certain extent. It's just that I didn't fully break it. Now I take that specimen and give it to another tester. That tester, this new person, has no idea that this specimen has been previously tested. And he puts it into the lab and he does a tensile test experiment. And what he will observe, first of all, is that, well, it will have a slope in the elastic region that is similar to the original specimen. But when it starts to yield, it's going to start yielding, right? The first specimen probably started yielding over here. The second one, however, is going to start yielding at a larger stress. Why? Because eventually all of them have to do with the same stress strain curve. So the second specimen is going to go here and it's going to start yielding. And then it's going to try and break, but it's going to break earlier because the amount of deformation to failure for specimen A is that much, whereas for the green specimen, it's this much, it's less. It comes from the original stress strain curve, so it's going to take less amount of deformation to break that new specimen. So then I look at specimen C. What have I done? I've taken the raw specimen, I've deformed it, but not all the way to fracture, and then I've unloaded it. The amount of deformation that it experiences is more than specimen B, and then I take that specimen, give it to a third person now, and that third person does an experiment with it, and he observes a stress strain curve that goes in the elastic region with the same slope, but it starts yielding at a larger stress than green and red, and then it has a smaller amount of deformation to failure. How do I know that? Because if I unload back, I will go eventually along the same curve up to failure. Now here I've modified the failure stresses a little bit, but the point that I'm making here is that typically what happens is that when you deform a material plastically, it really gets harder to deform, first of all, because the stresses that you have to apply they are continuously increasing. But also, two strange things happen. We're not going to directly model this, but two strange things happen that are very important for manufacturing and modeling steps. Now, one, the ductility of the material decreases with deformation, and two, the yield strength will keep increasing. Okay, so when you deform a material plastically, strength increases. With strength, I'm meaning here the yield strength, but ductility decreases. Larger strength is something that's usually desired, so it is usually something that we want. But ductility is something that we really do not want. We want things that can deform as much as we want them to. This is particularly important for manufacturing when you want to deform metals into very strange shapes. So lower ductility is not desirable. So the whole process of material science that goes hand in hand with mechanics is to design metals that can display large strength and also high ductility. And that is something that is not easy to achieve. So this is just to give you a perspective of two things. One, that materials do get stronger, they harden with plasticity. So hardening refers to the increasing load or stress that we need to apply to deform the material further. In practice, when you deform the material, really, in some sense, its yield strength is also increasing, but remember, its ductility also decreases. So these are qualitative concepts that we need to keep in mind.